Hello, good morning. I SEEMA GARG, Associate Professor in Chemistry, SPC Government College, Ajmer. Today, video 143. It is for BSc Part 1 Organic Chemistry, Paper 2, Unit 1. Today, we will discuss some more aspects of structure and bonding, bond length. The minimum distance between the centers of nuclei of the two bonded atoms at which the attractive and the repulsive forces just balance to each other and the potential energy of the system becomes minimum is called the bond length. According to Pauling, the length of a covalent bond is equal to the sum of the covalent radii of R of the bonded atoms. So bond length R radii in between the A and B atoms is equal to radii of A plus radii of B. Bond length can be determined by the X-ray diffraction, electron diffraction, or spectroscopic methods. The magnitude of the bond length depends upon the following factors: size of the atoms. For example, as the size of the halogen atoms increases, the bond length of carbon halogen bond increases. For example, carbon iodine in between that carbon iodine bond having higher bond length compared to carbon bromine, carbon chlorine, and carbon fluorine. So it depends on the radius of the nuclei. Second point, multiplicity of the bond. As the multiplicity of the bond between two atoms increases, the bond length decreases. Carbon-carbon single bond having higher bond distance or bond length 1.54 angstrom, carbon-carbon double bond 1.34 angstrom, carbon-carbon triple bond 1.20 angstrom. So it is decreasing with the multiplicity of the bond. Second point, bond angles. Polyatomic molecule contains more than one covalent bond. Each covalent bond is formed by overlap of atomic or hybrid orbitals. Since atomic orbitals except S, P, D, or F are directional in nature, therefore covalent bonds make angles between them. Thus, the angle between any two adjacent covalent bonds in a polyatomic molecule is called the bond angle. Bond angle depends upon the following two factors: the number of shared and lone pairs of electrons around the central atom in a molecule. For example, methane, ammonia, and water. See here, bond angle between the hydrogen, carbon, hydrogen, it is 109 degree 0.28 ounce, whereas in ammonia, it is decreased to hydrogen, nitrogen, hydrogen, it having 107 degree, whereas in water, hydrogen, oxygen, hydrogen bond angle is 104.5. Type of hybridization. This is due to the reason that the pi electrons being less tightly held by the carbon atoms repel the bond pair of carbon hydrogen bonds more than bond pairs of the carbon hydrogen bond repels each other. Bond energy. Whenever covalent bond is formed, some amount of energy is always released. Conversely, the same amount of energy will require to break the bond. There are two kinds of bond energy, bond dissociation energy and bond dissociation energy. The amount of energy required to break 1 mole of hydrogen molecule into individual atoms is 104 kilocalorie per mole. Water molecule to hydrogen to hydroxy 118 kilocalorie per mole. Oxygen hydrogen, it is 100 kilocalorie per mole. Similarly, methane, bond dissociation of methyl plus hydrogen, bond dissociation energy 102, methyl to hydrogen D2 105, methyl to CHH D3 108, CH carbon hydrogen D4 83. Bond energy D1, D2, D3, D4, it is divided by 4. So carbon hydrogen bond energy is sum up of this all and divided by 4, it will come 99 kilocalorie per mole. So bond energy depends upon the following factors: size of the atoms, carbon, chlorine, like that, the size of the atom, its bond energy is changing. In carbon fluorine bond, it is about 107, carbon chlorine 80, carbon bromine 69, whereas carbon iodine 50.9 kilocalorie. As the size of the atom forming covalent bond increases, bond length increases but bond energy decreases. Multiplicity of the bond. As the multiplicity of the bond increases, the bond length decreases and hence the bond energy increases. For example, carbon-carbon bond length is about 1.5 fold is higher compared to carbon triple bond. But its bond energy is less. It's about 83 kilocalorie per mole, whereas carbon-carbon double bond having 146, carbon triple bond having 199. Type of hybridization. Type of hybridization, carbon attached to the atom. Here it is carbon hydrogen having carbon is sp3 hybridized and carbon hydrogen sp2 carbon carbon sp. So their bond energy is also changing according to the type of hybridization. As the type of hybridization is suppose here in sp, S character is more, so its bond energy is also higher. Similarly, here multiplicity of the bond is also affecting on the bond energy. Carbon-carbon bond length is higher, S character is less, so its bond energy is also less. So this is also factor responsible for its bond energy. Shorter bonds are, as we have seen that increasing S character shorten the bond. It follows that bond strength increases with increasing S character. Double bonds are both shorter and stronger than the corresponding single bonds, but bond energy is not twice because of pi electrons. Sigma bond is stronger than the pi electron bond. So this is about the bond length, bond angle, bond energy. Thank you very much for today's lecture.